Good morning, everyone. I am Dr. P. Kritika, working as Assistant Professor in the Department of Civil Engineering, SRM Institute of Science and Technology. Today, we are going to study about the basics of tall buildings. That is, how the tall buildings resist the lateral forces and how it has been resisting all these forces. We understand weight. We have been building with gravity for over a millennium of years. Those are the forces that truly define tall building, that is, wind and earthquake. The system we choose to resist these lateral loads shapes everything: the floor plan, the facade, how high we can go, and ultimately how much it costs. From moment frame to dive grids, each structural system offers a distinct balance of stiffness, flexibility, and constructability. Understanding these trade offs is what separates a building that merely stands from a building that truly performs. So let's start. The lateral loads challenge. So let's start with the core problem. As buildings rise, wind forces rise. Seismic forces also, it doesn't rise, it become the dominant design driver. The choice of lateral system isn't a secondary decision made after architecture. It shapes everything. Let me break this down into three critical aspects. First, wind loads. Wind is a dynamic pressure and it increases dramatically with height. At street level, you might feel a breeze. At 400 meters, you are in a complete different wind region. This drives two things: how much the building saves drastically, horizontally, and occupant comfort criteria. Because people don't want to feel like they are on a ship in a storm. Secondly, seismic loads. Earthquakes generate inertial forces. The ground moves, the building wants to stay where it is, and the resistance creates enormous forces. We need systems with ductility, that is, the ability to deform without breaking. The energy dissipation capacity, the ability to absorb and dissipate that seismic energy. Drift control, that is a third driving criteria. That is, excessive sway isn't just uncomfortable, it causes facade damage. Cracking of cladding, failure of sealants, it can damage interior partitions, elevator alignment, and even mechanical systems. So, controlling drift is both a serviceability issue and also a durability issue. So, why does a 10-story building not need to worry much about wind sway, but a 60-story building absolutely does? The answer lies in the relationship between height and lateral stiffness. As height increases linearly, lateral deflection increases by the cube or even fourth power, depending on the system. So, small increases in height create massive increases in sway. This is why lateral systems are the heart of tall building design. So, firstly, moment resisting frame. The simplest lateral system is moment resisting frame. How does it work? Beams and columns are rigidly connected. When lateral loads push the building, the frame resists this push through bending. The beams bend, the columns bend, and the rigid joints transfer moments between them. It's elegant in its simplicity. It is best for buildings up to roughly 20 stories. Beyond that, the system starts to struggle. The tremendous architectural flexibility is its major advantage. Open floor plans, large windows, minimal obstruction. This is the system architectures love. You can place walls wherever you want. You can reconfigure interiors easily. The structure doesn't dictate the architecture. But what is the limitation? Lower lateral stiffness. As height increases, sway becomes excessive. Drift controls the design. You end up needing enormous beam and column size, which becomes economically and spatially inefficient as well. At some point, you are throwing more and more steel at a problem that is a different system could solve more elegantly. Think of it this way: a moment frame is like a person standing against a strong wind. By just flexing their knees, it works for a while, but eventually you need to plant your feet wider, brace yourself, you need a different strategy, right? So moments frames a starting point. There where we all begin. But they are rarely where it all begins end. So what happens when we need more stiffness? So what happens when we need more stiffness? Without jumping to concrete walls, we add bracing. How does it work? Diagonal members create triangulated panels. Now, lateral forces are transferred through axial tension and compression in those diagonals, not through bending, but axially loaded members are incredibly efficient. A thin steel rod in tension can carry enormous loads. So the major advantage is high stiffness at low cost. This is one of the most economical lateral systems available. You are getting a lot of lateral resistance for a relatively little material. But what is the limitation here? These triangular bracings, abstract openings, windows, doors, circulation path, they all have to work around the diagonal members. This is the classic tension between the structure and architecture. The structural engineer wants diagonals everywhere, but the architect wants clear views and open paths. There are variations, of course, X bracing, highest stiffness, K bracing and V bracing. They allow larger openings by meeting at a central points. Chevron bracing is another which keeps the ground floor open, but the fundamental trade-off remains stiffness versus architectural freedom. Whenever the stiffness is more, architectural freedom gets reduced. So braced frames are common in commercial buildings where some obstruction is acceptable. Industrial buildings, office towers with repetitive floor plates, but in a luxury residential tower where every apartment want floor to ceiling windows, bracing becomes a harder sell. This is where we start seeing the structural system selection is much about program and user experience. And there is another alternative, shear wall system. So it is a system which is pure of stiffness. Solid reinforced concrete walls carry lateral loads. They are on thin partitions. These are substantial walls, often 200 to 400 mm thick, extending continuously from foundation to roof. They act as a deep cantilever beams resisting shear and moment. The strength, obviously, the excellent lateral stiffness and drift control is there. In high wind and seismic loads, shear walls are often the go-to solution. They limit sway dramatically. They provide a sense of solidity that other systems can't match. They severely restrict floor plan flexibility. You cannot put a door through a shear wall without major structural consequences. You can't have an open plan that cuts off through a shear wall. The wall locations dictate the architecture. This is why shear walls are common in residential towers and hotels. Buildings where wall locations naturally align with unit partitions. Every apartment has walls anyway. If those walls are structural, it is a win-win. The architecture and structure align. But in an office building that needs large, open, reconfigurable floor plates, shear walls become a burden. You end up with a central core of walls and limited perimeter flexibility. It is a system which teaches us the best structural system is one that aligns with rather than fights against the architectural plan. When structure and architecture are in harmony, both perform better. The perimeter frame carries the gravity loads. It's a division of labor. The core acts as a deep cantilever beam. Imagine a concrete box rising from the ground, resisting wind like a tree trunk resists wind on its branches. Meanwhile, the perimeter frame can be lighter, more flexible, because it is not doing the heavy lateral lifting. But whatever the limitation, limits planning at the building center. Large open spaces must work around it. You can't have a grand atrium through the core. You can't have a column-free ballroom at the center. The core is non-negotiable. Negotiable. But there is a thing. In most tall buildings, you need a core anyway. You need elevators, you need stairs, you need mechanical shaft. So the frame core system doesn't create an obstruction. It leverages an existing necessity for structural benefit. It is one of the most common systems in modern tall buildings, particularly in 3260 story range. It's efficient, proven, and relatively straightforward to construct. Burj Khalifa, for all its complexity, still uses a core based system at its heart. The frame core system represents a mature understanding of tall buildings' behavior. Let each element do what it does best. Next comes the tube system. Now we enter the realm of very tall buildings, 50 stories and above, and the system that made them possible, the tube system. The entire perimeter becomes a rigid tube, like a hollow box column. The closed space columns and deep spandrel beams create a continuous structural shell. Lateral rolls are resisted by the tube, acting as a cantilever, and the interior completely open. No columns, no bases, no walls. This was revolutionary. Before the tube system, very tall buildings needed heavy interior structures that fragmented the floor plate. The tube system said, move the structure to the perimeter, make it work as a shell, and free the interior. And who is this pioneer? Fasser Khan. At the Skidmore, Owens and Merrill in 1960s. He is arguably the most important structural engineer in the history of tall buildings. His tube concepts, framed tubes, tube in tube, bundled tubes, extended the practical heights of buildings by hundreds of meters. And few examples, the John Hancock Center in Chicago, the Willis Tower, formerly Sears Tower, which uses a bundled tube system, 9 tubes of varying heights creating that distinctive stepped profile. But what is the limitation of it? Complex to construct. The connections are demanding. The tolerances are tight. But for height, it's transformative. The tube system teaches us rethinking the fundamental structural concept. Not just scaling up existing systems, is how we break through height barriers. And here comes the next outrigger and belt truss. As we push into super tall territory, 300 meters and above, even tube systems need help. There comes our hero, outriggers and belt trusses. How does it work? Outriggers are rigid arms, typically steel truss or concrete poles that connect the central core to perimeter columns at specific levels, usually mechanical floors. And belt trusses tie the perimeter columns together at those same levels. And the result, the entire building perimeter engages in resisting lateral loads, not just the core. Think of it as this way: without outriggers, the core is like a person trying to resist a push only with their spine. With outrigger, it is just like a person planting their arms against a rigid ring. The whole body engages. It is best for super tall buildings where drift control is critical. When you are building 400, 500, or 600 meters tall buildings, every millimeter of sway matters. Outriggers are one of the most effective tools for controlling the drift. This is where things get complex. Outrigger flows require precise integration of structural, architecture, and mechanical system. Those mechanical flows aren't just housing equipment anymore. They are structural battlegrounds. Every discipline needs to align. You can't just add an outrigger without thinking about where the elevators go, where the ducts run, where the facade breaks. It requires integrated design teams working from day one, not sequential handoffs. Outrigger represents a point where tall buildings design becomes truly interdisciplinary. Structure alone isn't enough anymore. And next, diagram and hybrid systems. Finally, let's look at the cutting edge. Instead of vertical columns and horizontal beams, the exterior is a diagonal grid. The diagonals carry both gravity as well as lateral loads. This eliminates the need for many vertical columns. The result is visually striking. The buildings like 30 St. Mary Axe in London, known as Jerkin, use diagram principles. Structurally efficient, architecturally expressive, but complex fabrication and erection rise cost significantly. Every joint is unique. Every diagonal is precisely angled. The tolerance or unforgiving. Diagrams are beautiful, but they demand craftsmanship at scale. This is where we combine multiple approaches coal, frame, outriggers, tube into a single optimized system. For super tall buildings, hybrids are increasingly the norm. The Shanghai Tower, for instance, uses a core, a double skin facade that acts as structurally and outriggers is not one system, it's a synthesis. And what is a challenge? Design complexity, of course. You need integrated teams, advanced analysis software, and often full scale testing. Margin for error shrinks. The coordination demands a span, but for performance, it's quite optimizing. Hybrids allow us to push heights and no single system could achieve alone. Digrids and hybrids teaches us a final lesson. The future of tall buildings lies not in choosing one system, but in intelligently combining many. So, this is a very big question. How do we choose? And let's have a quick reference. Moment frame, it's up to 20 stories. And next brace frame, it's up to 40 stories. While shear wall, it's up to 50 stories. And frame core from 30 to 60. And tube system goes above 50 stories. Wherever outrigger and belt as well as dagger and hybrid, these two systems are mainly for super tall structures that is more than 300 or 600 meters. So frontier of tall building design lies here. But remember, no single system is best. The right choice balances three things: structural performance, architectural intent, and structurability. The system that is structurally perfect but architecturally unworkable is a failure. A system that is architecturally beautiful but impossible to build is a fantasy. The art of tall building design is finding the sweet spot where all three of this align. Height drives a structural need, program drives spatial need, budget drives constructability need. But the best engineers are those who can navigate all three simultaneously. To summarize, what we have covered today is lateral loads and challenge. That is, which is the lateral loads that dominate tall building design. So there are totally 7 structural systems from simple moment frame to complex hybrid. Each system offers unique balance of stiffness, flexibility, and constructability. So system selection is not an integrated decision, but engineering and also architecture. Thank you.